All right, people, let's take a quick look here at question number 3. It says the empirical formula of a compound of phosphorus and oxygen was found to be P2O5. Experimentation shows the molar mass of the compound is 283.89 grams per mole. What is the compound's molecular formula? Okay, so let's think about this here. We need to know the difference between empirical formula and molecular formula in order to answer this question. Remember, empirical formula is the smallest whole number ratio, but molecular formula is the actual or true ratio of the elements in that compound. So basically what we need to do here is we need to think to ourselves, all right, we've got P2O5 as my empirical formula. What is the molar mass of this thing? And let's compare that then to the molar mass of the actual compound. So again, I'm going to take a look first at phosphorus here. I've got 2 moles of phosphorus. And for every 1 mole of phosphorus, I have a molar mass of 30.974 grams, which means that I have 61.948 grams of phosphorus in 1 mole of this compound. If I do the same thing with oxygen, I've got 5 moles of oxygen. And for every 1 mole of oxygen, I have a molar mass of 15.999 grams. 15.999er. Oh man, let me use my calculator here. 5 times 15.999. Enter. 79.995. 79.995 grams of oxygen. Okay, which means that the molar mass of this empirical formula, this P2O5, is the sum of these two. So there's my 79.995. I'm going to add to that the 61.948. And we get 141.943 grams. Whew. 141.943 grams is the molar mass of P2O5. Okay, so that's the molar mass of my empirical formula, but experimentation has told us that the compound's actual molar mass is 283.89 grams. So, what is the molecular formula? Is it P2O5 or is it some multiple of that? Well, all we need to do is take the 283.89 grams per mole and compare that to the molar mass of the empirical formula, the 141.943 grams per mole. Now, this one, again, depending on your math skills, you may be able to figure out what the relationship is between these two without using a calculator. And I encourage you to, whenever possible, think about how to solve these problems without using a calculator. So cut off some decimals if you have to, round if you have to, estimate, especially when it's multiple choice. You can get away with quite a bit. But if you're unsure, you can always go to your calculator. 283.89 divided by 141.943 equals. So what this tells me then is the molar mass of the actual compound is twice as large as the molar mass of the empirical formula. And so in order to get the molecular formula, I just need to multiply my empirical formula of P2O5 essentially by a factor of 2, which then means that this becomes P4O10. And this is my molecular formula. Again, keep in mind, molecular formula is what the true or actual ratio of moles of the elements is in the compound, while empirical is the smallest. So P2O5 is the smallest ratio, but P4O10 is what it actually is. And if you're unsure, you can always check. Add together 4 moles of phosphorus and 10 moles of oxygen and see if you don't get 283.89. You do. Alright, so the last one on the block for us here, a sample of a compound with a formula of 34.00 AMU is found to consist of 0.44 grams hydrogen and 6.92 grams oxygen. Find its molecular formula. Okay, so again, we want the molecular formula. And we're told that the formula mass of that compound is 34.00 AMU. Now recognize here that the molar mass is identical in the numerical value, but would be represented in grams per mole. So anytime you see that formula mass in AMU, recognize that it's also the molar mass, but in grams per mole. And that makes your life a little bit easier here in the macroscopic world. So as we take a look at this, again, we're trying to find the molecular formula for this compound. We can't find the molecular formula directly. We have to always go to the empirical formula first and then compare it to the molar mass, or the mass of the actual formula. So if we do that, we're going to take, again, our masses, 0.44 grams of hydrogen, which is just coming from right here. And I'm going to convert that to number of moles, grams hydrogen, moles hydrogen. I'm going to compare that to 6.92 grams of oxygen. And again, these values will come from the masses on the periodic table, which is always going to be the mass in 1 mole of that element. So if we take a quick look, hydrogen's molar mass is 1.008, oxygen's 15.999. We plug those values in, 1.008 and 15.999. I'll do the first one here on my calculator, 0.44 times 1 divided by 1.008 means that I have 0.44 moles of hydrogen. I do the same thing with oxygen, and you get 0.433 moles of oxygen. And then it comes down to comparing. How do moles of hydrogen compare to moles of oxygen? Well, hopefully this one's really easy to tell. Oh, that ratio or that relationship is a 1-to-1 ratio. But if you're ever unsure, you can always, just divide by the smallest molar amount. In this case, the smallest molar amount is the 0.433. In this example, we get exactly 1. And this one here, we'll do this one on our calculator, 0.44 divided by 0.433. We get 0.016. So it's a little bit, if we use significant figures, it's going to be exactly 1.0. But again, it's within the 1/10 of a mole here, so it's close enough that we can just round down to 1. So the empirical formula, empirical, is HO. Now I'm feeling really good about myself. I solved for the empirical formula, but this problem is asking us for the molecular formula. And so how does this mass compare to the mass of the compound, which we find to be 34.00? So to take a look at this, the mass of this empirical formula, 1.008 grams, because there's just one of each of them here. It's pretty easy to do, 15.999 grams. Which means that the molar mass of this compound is 17.007 grams per mole. That's the empirical formula mass. Now, if I compare the 34.00 grams per mole to the 17.007 grams per mole of the empirical formula, we can determine that the mass of the molecular formula is twice as large as the mass of the empirical formula, so twice as large. So if I know my empirical formula is HO, the molecular formula is going to be twice that, which means that H2O2, or hydrogen peroxide for you nomenclature geniuses out there, is the formula for my molecular compound. So molecular formula for this compound. And we're done.